In this video, I'm going to talk about databases and provide a brief introduction as to what they are, where they fit in the architecture, why we might need to use them, what they look like, that sort of thing. So in the architecture, they fit in the back end with the application server. So we've already been through the user front end with HTML, CSS. We'd also have JavaScript in there. And the user uses this user interface to interact with the back end to ask for services, data or whatever. And the application server will contact the database server and ask it for information to return to the user. The user may be wanting to add some information like someone's name and address, etc., in which case they will type it in here, then push it down to the application server, which would then write it into the database server or into a database, into database tables. Okay, the database is set up and administered privately, because we don't want the database, which contains probably personal data, we don't want that to be exposed to the internet. So it's hidden behind the application server. That's why it tends to be drawn like this. So it's hidden behind the application server, so we need a different way in for administrators, although I don't know if I spelled it with 2 Ds, but anyway. So administrator can have a secure connection directly into the database, and that's why it's drawn with a dotted line. So they would have sort of secret credentials and an encrypted separate channel to everybody else that they can gain secure access to the application server and the database service, so they can do things like upgrade security patches or make changes to the database for whatever functional reason. So they're the admins. Alright, so what is a database? It's an organized collection of data that's stored, accessed electronically, typically managed by a database management system, or DBMS. And there are various types. So I'll just have a quick look at the common ones. I'll illustrate a couple of the very common ones and discuss a third commonish one. Relational databases, then, these are very common. These are tables with rows and columns like a spreadsheet. The columns are the letters in the spreadsheet, you'd normally see A, B, C, D or whatever, and the rows are the numbers down the side, and the data in the cells. So very similar to a database table. Alright, databases enable efficient data storage and retrieval using the structured query language, or SQL, or some people call it SQL. So that's a language, a fairly basic language, that enables the reading of data, modification of data, updating of data, deletion of data, using a fairly straightforward-ish language. Not what you could probably call a programming language, but it's been designed to access data in a structured database. I'll talk about it shortly. It's popular in systems requiring very accurate and reliable data processing. Popular when data entities have strong relationships to each other. Data entities, for example, like customers and products. Customers buy products, so there's a strong relationship between customers and products, because customers buy products, products are bought by customers, and the data for customers, for example, is quite structured. You typically have a customer ID, a name, address, postcode, probably telephone number, various other such like information where all the customers will probably need to provide the same information. and this is what I'm saying here about it being highly structured, fits neatly into rows and columns, where every row has to have exactly the same number of columns as all the other rows, and the type of data that's added to those columns has to be the same for every row. So for example, if a row has a first name and a last name and an address, then every row, even if there's millions of them, have to have a first name, a last name and an address. Oh, that's what that says. A schema is basically a description of the type of data that can go in a particular column. I'll discuss that in a minute when I create a database. The use cases for this type of database are finance, inventory systems, customer data, health records, things that are very structured, and things that require guaranteed data consistency. I'm not going into the detail of all that, but very popular in banks and other financial institutions and government departments. So popular RDBMSs include MySQL Server, Oracle, Postgres, and various others. I'll talk about MySQL Server, a very popular relational database for web development. Demo, right? Create a database and do some SQL. Okay. So I've got MySQL Server installed, and here is the graphical user interface associated with it. So I can log into the database and create log into the relational database management system, and within there I can create multiple databases, and you can see there's quite a few different databases in here. All right, so I'll just create a new one. So I'll create a new database. You don't have to follow how to do this. I'm not expecting you to have to do it. I'm just showing you a sequence of events and what this stuff looks like. So I'll call this one junk, then I can delete it later. I need to apply that. Apply. So I should now have a database called junk here. Tables, there are no tables in it. I need to create a table. I need at least one table really. So I'll create a table and I'll call this one junk as well. All right, so what we need is a table where each row is uniquely identifiable. So for example, it might be a national insurance number, or it might be a staff number, or something which uniquely identifies an individual, or a product. So it could be a product code or whatever. So you normally have one column that will uniquely identify any row within the whole of the table. So I'll call this ID for the sake of calling it something. To keep it simple, I'll create it as an integer, which is just a whole number, and I'm going to tick this box here that says it's a primary key. This is the primary identifier for all my rows. And then means it's not null. I've got to have one. If I don't have a unique identifier, I'll never be able to find the data in the row. So I don't want any of these to be null, in other words, empty. And I want to keep it simple and auto increment. So every time I add a new row in, it'll just update the ID. So it'll start at 1 and go 2, 3, 4, 5. So they're all uniquely identified. Okay, so that's the first row, first column, sorry. Second column, then I'll say call first name, and we can say how big a name do we want. And this is saying you can have up to 45 characters. You can change that to whatever you think is sensible, but I'll stick at that. I don't mind for this demo. And last name, I'll leave the same. And then let's have age as well, age. So I can show you that. We can have a different type. age is going to be an integer because it's a whole number. And each of these, I need each person to at least have a first name and a last name and an age. So I need to make sure that these are not null. So if you try to enter a record which doesn't have somebody's first name, last name, or age, then the database management system will stop you from doing it. Okay, so I'll apply that. And it says it's done it. So in here now we should have a table called junk. So if I look at what's in this table, there is nothing. It's just an empty table. You can see it's like a spreadsheet. It's got columns at the top. The schema of these columns is that one's an integer which auto increments and it's a primary key. This one's a string of characters up to 45. So is this, and this one's an integer as well. So every row has to have data that maps to that schema, to that setup. So every first name can only be a maximum of 45 characters. So every first name and every last name, every age has to be an integer. You can't have an age of 25.3. All right. So I'm not going to add a value in for the primary key because I've just set it to auto increment, so it'll do it. It'll do it for me. So I put the names in. Like if Russell has 1 or 2 L's. Let's see what age is he, I don't know. Probably being generous. Oops. Let's say that's near enough. I might have got 1 or 2 of those ages the wrong way around. But anyway, I'll apply those changes to the database. And so they're now in there. They've got their unique IDs. So number 2 is me, number 3 is Joe Soap. And we can identify those people in that way. All right. So the structured query language, you can see I've already been using it from here. I want to show all the columns and all the rows in this table. So I'm going to say select. Star means everything, every column and every row from the database called junk, table called junk. Now I can double click this and it means I don't have to specify the database every time. It means it'll assume it's that database by default. And I can execute that SQL query. Press that button and it gives me everything. I could change that. I might think, well, I don't really want the ID. I don't want to be giving away people's national insurance numbers or whatever. I just want these 3 rows here. So you might want to say select first name, last name and age from the table junk. Oh, I think about the type down there, wouldn't you? First name, last name. And so that's what it brings back. So we can use this query language here to interrogate the database. A database would normally contain more than one table. Quite often they contain lots of tables. Let's look at this one. Tables. This one's got a few tables in it. It's a bit more of a businessy like one. It's got customers, notes on the orders, order items, order statuses, such like that. So we can do exactly the same thing we've done with this database. We can query it with, let's close this stuff down. So I can say, let's have a look at the customers. Do a select on the customers. Select star from customers. These are all the people who are in this database. And there's orders. Let's see what they've been ordering. Now these are just order ID, product ID, and the quantity. So 10 of these things have been bought. And these things are in a different table and referenced by these numbers. I'll not get involved in that, but these are called relationships, where this table is related to other tables. So it'll reference the number in the other table. So for example, in this order number 1 has 4 of product ID number 4. So we go into the products tables, then we can find number 4. It's whatever that says, broccolini, Geylan, Chinese, whatever that is. So, and they cost £4.53 or $4.53, wherever this database came from, I can't remember. So the idea is that the orders are related to the products. So if you notice down here, so somebody bought 7 of these things, and what are they? They're item number 3. 7 of these, item number 3. Item of products number 3. Lettuce, romaine, heart. There's 38 in stock. So they're related to each other. And so this, as I explained before, the first column is the primary key that uniquely identifies each row. But here, this is also a key which is linking to that other table. This is called a foreign key and forms a relationship between these two tables, which makes this a relational database. So if you hear the term relational database, this is what it means, that these tables are related to each other by a foreign key. Okay. So going back to the slides then. Remember the diagram here. Then what I've been doing is I've been looking at the database, but it's actually on my laptop. It's a local database just on my laptop only, so nobody else can see it. But then you might think, oh, that's private, but it's also of no value because nobody else can access the data. So what we tend to do is then, once we've tested and got it working, we would deploy it to a remote machine. Could be an on-prem server, but these days more likely on the cloud, such as AWS or Azure or something similar. So we've looked at the front end previously, and so I'll look at that again. This is the joke example, and the idea is that you press the button and you get a joke and it displays the punchline. So what happens is we are making an API call from the browser to the back-end application server, and we're asking for a joke of type general, and we want one of them. If we want a joke of type knock knock, we'd ask for a joke of type knock knock. We'd send that information to the back end and say, find me a joke of type knock knock, and it should bring one back. So the application server has had to interrogate the database and say, give me a list of jokes of knock knock type, and then it'll pull one out and send it back to me. If I wanted more of them, then I've asked for 16, and so it's pulled all the ones it can find. 1, 2, 3, 4. There's only 5 of them in there, so it's tried its best and sent me all of them. All right. So the point I'm making here is that all this stuff, like this is the, I mean, you wouldn't normally dump a table with this amount of data in it, but I'm showing that there's the ID of the table, the type of joke that's in the table. These are columns in a joke table. So I'll show that by logging into the joke table and finding this table, joke database, and finding this table. So go back to the MySQL server, and currently I'm connected to a local instance. I'm going to connect to that remote instance. connection name, I'll just call it remote. And we want to connect to it. We can't just connect to it simply like this. I'm now an administrator. I need to log in securely through that dotted line that I showed in the diagram. So I need to create a secure connection. So I'm going to use this SSH secure shell approach. So there's a bit more stuff to fill in. So what is the host name? Well, the host name is the IP address that I used, which is the IP address of the virtual machine that's running in Azure. So that's that. Copy it from the browser, it copies all this stuff as well. And you want the IP address. Thank you. What is the username of the machine? It's me. What is the password? Well, there is no password. I've used a secure file with a secret key, so I'll just have to find that. And in alphabet. Azure. Okay, so it's going to look up the secret key in that file. And then what's the host name at the other end? Well, I'll just leave it as that. That's the IP address at the other end. What's the port number? The port number I'm connecting to, I think it's 4000. The username for my database, I'm an admin, so I've called myself admin. I need to provide a password. And I should have tested this first, really. Oh, fortunately it works anyway. Right, okay, so it's saying you've connected. And so if I should now see a new connection. So I can log into the local instance and find the local jobs database, or I can log into the remote one. So here, this is it logging into the AWS, the Azure server in London. And here, I've only got a single database. If you look at the local one, you can see it's different because I've got loads of databases in there. But here, I've only got one because that's all I need. And it's got tables, 2 tables. One's got jokes in it, so let's do a select on the jokes. Here's all the jokes. And you can see there's an identifier. That's the public, the primary key. There's this type field. What type of joke is it? It's type 1, 2, 3, 4 or whatever. It not very easily readable. Then the setup and punchline. The reason that these are numbers is because, as I showed you before, this is actually a foreign key to a different table. So these jokes here are referencing joke type 1. These are referencing joke type 2. So let's have a look at the types table. And you can see joke type 1 is general, joke type 2 is knock knock. So the 2 tables are related to each other, and they're joined to each other via this foreign key. So this one's a primary key, this one's a foreign key that references a different table, this table. All right, let's close these down. Close all. Right, what I'll show you in here. So we can do exactly like we did before. We can use a select star to get what you want, or if you just wanted the setups for some reason, then you can just say give me the setup, and that's all you get back. So you can see this is pretty readable, pretty easy. Let's say we wanted all type 2, so let's look at the type table again. Type 2 is knock knock, so we wanted all the knock knock jokes then. So select star, so select all the columns, save me typing it in, from jokes. So I can stop on to keep typing that in all the time. First double click that and say make that the default. From table jokes, where in fact what I'll do is I'll do that first, and then we can see what the columns are called again. Okay, so I only want the ones of type 2, so where type equals 2. Doesn't seem to like that. Can't see anything wrong with it. See what it says. Got an error in my SQL syntax. From tables. Oh, I thought I typed that in once. Where type equals 2. Okay, so it's pulled back all the type 2s, and it's 1, 2, 3, 4, 2, 4, 5, which is the 5 I showed you before. 1, 2, 3, 4, 5, and you can see their IDs: 12, 14, 13, 61. So they're all in there. These have been brought back randomly. Right. Now, it's not very user-friendly to have to refer to table to type 2 or type 3 or whatever, because you'd have to remember what they all meant, because all the actual definitions are in different tables. So what we can do is we can join the two tables together, and then select the columns from the two joined tables. If I put this in, select, what do I want? I want the setup, which is here. I want this row, column. Punchline, yeah, I'll need that. And type from the jokes table, which is this one. Put the description of the types in a different table. So I'm going to say join. Put join down there, and you can see it. Join with the table type, this one. So I'm joining these two tables together to make the query. All right, so from those two tables, what do we actually want to join them on? What is the relationship between them? We know they're related by this field here, this foreign key, and the primary key on this side. So all the number 2s here are referencing the primary key number 2s on here, knock knock. So on the table type ID, which is this one, this is table type, that's the ID. I need to reference this one here, which is type programming. Oops, sorry, look at the one. The table jokes type, this one here. So we're linking those two fields together. All right, well, now we've linked the two tables together. We've said what the relationship is between them. Which ones do we actually want? So we can say where. So we want them all these columns and these two tables, which are linked through these keys, where the table type, this one here, type, so we can make reference to the actual words this time, equals programming. So I'm going to come back, pull back all the programming jokes. Instead of saying 3 or whatever programming is, we can type the word programming in this time. Let's give it a go. Now, got an error in your SQL statement. Oh, I don't have an error in my statement. Just pressed it and it didn't change anything, and it worked this time. So this is always something a bit flaky about this user interface. Anyway, so this worked perfectly well. All right, so that's joining two tables through their relationships. And so I've been able to reference programming. So we wanted the not ones, for example. I can make it much easier to search the table up, because I can write exactly what field name I want in the related table. So this time it's pulled back all the not jokes. And then these are the ones that get returned through the application back to the user who requested them here. So basically, when we're typing in not add jokes, then we make this request from here with an API, and the request comes in from the application, to the database to say, give me all the dad jokes. So it's going to execute a query like this. Dad. It'll query the database. There's only two. It's going to bring both of those jokes back, and then you'll see it will bring them back. Dad jokes one. And there's the two jokes there, look. So that's how it works. That's how the relational database works. Of course, there are other queries, such as inserting data into the database and deleting data and updating data that's already there. But this is just an introduction to this, just to give you an idea of what's going on. All right, so we got down to here. So that's the relational database management system. So I talked about database management systems, and this one was a relational database management system, which I talked about the relationships between tables using a foreign key that references the primary key in a different table. All right. Document database then. Document database is generally used when there isn't a fixed structure to the data. And this is one of a series of databases known as No-SQL or No-SQL databases, because they're not generally accessed using the structured query language, because they're not structured databases. They've got their own way of accessing data. So data can be semi-structured or unstructured, but it's not going to have rows and columns in the same way that the relational database does. So not every row has to be the same. So not every row has to have exactly the same columns as the previous one. In fact, we don't even use rows. There's no need for a fixed schema. In other words, we don't have to specify exactly how many characters there are in first name or last name or that sort of type of restriction. Now, that makes it more flexible, but there are downsides to it as well. With every positive, there's usually a negative. It's very easily scalable, this type of database, so it can hold huge amounts of data. And use cases include things like product catalogs, where not every product has the same attributes. So I'm saying here phones. Phones might have, should we say, details such as battery life or 3G, 4G, 5G functionality, or whatever else you want to put in a phone. And not all phones have all the same information stored against them. But you might have products like socks. We don't have 3G, 4G, and 5G socks, for example. Socks might just have a size and a colour associated with them, but they could be in the same table because they're still products. If they were a relational database table, we'd have to somehow put a column in for every one of these. Every row would have to have the same columns, which would make this quite tricky or wasteful. So these document databases can be quite useful for unstructured or semi-structured data. User profiles, for example. I don't particularly put very much in about myself on a user profile, if anything, apart from the necessary name and email address. But some people like to tell the world about everything about themselves in the user profile. And so not every user has to provide all the data in the same way. Okay, popular document databases include MongoDB. That's probably the most popular used today. But there are others: CouchDB, Amazon DocumentDB, Azure Cosmos DB. These are proprietary Microsoft and Amazon databases. MongoDB is very popular, non-proprietary. Well, I suppose they're proprietary to MongoDB, but it's not a cloud provider necessarily provision. Demonstrate MongoDB. Okay, so look at MongoDB then. See how it's different. So here's then called MongoDB Compass. This is the user interface for a MongoDB database, and I'll log into the local instance here. Okay, so it's connected, and these are the databases I've got on here, so I'll have a look at this one called books. Let's see what's in here. Books. So see, this time it's not written as rows and columns. They're just written as a list of attributes. So we've got a unique identifier still here. But then if you want an author, then just type author and write out, here it is. You want a title, put a title in. Now, as it happens, all of these have got author and titles, but they don't need to have. Pages, you could list the pages, you could have that in there or not have it in there. It's entirely up to you. If you want that here, we've got keywords. What's this one then? Alistair MacLean, it's action, war, espionage, and so we'd write it like this. You can see it's an array. Now, you know, we're familiar with arrays if you haven't done any programming, but you can see this is much more of a programmer's type database. And how you access the data in here is done more through programming than using a basic sort of separate language like the structured query language. And so this one's got keywords. What's this one got? Got some reviews in this one as well. So Billy loads of money. How to copy someone's GUI. Oh, I see. This is me having a go at Microsoft. So it's got keywords, and we've got ratings, and we've got reviews. One review. Steve Jobs, see you in court. That's just my sense of humour. All right, so you can see that the structure is very different. So each of these, what we would refer to previously as tables, we refer to as collections in MongoDB. So here's a collection of these things. One there, one there, one there. These are a collection of documents. So each one of these is a document. Strange name really, because it doesn't look much like a document. But anyway, there's a document, there's a document, there's a document, and the whole lot is a collection of documents. So refer to as collections and documents. To search them, you might say search by author. So we can just, you can see that the syntax is very much more program-like or programming-like. So you can search for author by name, or you might say, let me give me all the documents with a rating of less than 3. So I'm saying the rating is $LT less than 3. So I can do a search on that, and it comes back with these, and the ratings are 1, 2, 1, -3. Okay, so just still data storage and retrieval, etc. They're just structured differently and accessed differently. All right, that's the Mongo database. Graph database, I don't have one of these, but they're quite popular in applications you probably use and don't realize it. So they're represented as graphs. I don't mean graphs like you drew graphs at school, linear and logarithmic and you know, exponential graphs and stuff. These graphs are a different type of graph. These have got nodes represented by circles. They've got edges represented by lines and arrows. And they've got properties. The properties are associated with the edge. And so let's look at this example here. This is one of like a sat-nav type application where each node is a place, and each graph is each edge is a transition from one place to another. So we're going that way, and the properties associated with the edge are written there. So to go from place A to place B, whatever they might be, in this case it's a mile from A to B. If you're traveling at 35 miles an hour, it should take you 103 seconds to get there. And the objective is to get from A to F. And so you've got these relationships that you can get from A to B physically on a road. You can get from A to D on a road, and you can get from A to C on a road. But there's only those three ways you can go. There's only three roads from A. Okay, so we think, well, what am I going this way? Well, that's 2 miles that way, it's twice as far, but I can go faster. It's going to take me 160 seconds, so that's a bit slower. This one here is 4 miles, but I can go at 65 miles an hour, 221 seconds. That's still the slowest of all of them. So if you're looking for the fastest route, then the application would interrogate this database, get these details, and then try to work out the shortest path. Is it going to be ADF, or is it going to be ACDF, or ACEF? And these attributes will change depending on traffic conditions. So maybe during the rush hour, this one may be a far worse route, even though it looks direct, than this one. This one might be down minor roads, so there's not so much traffic. So the time may fall during peak periods or stay the same, whereas this one could increase. So these are relationships between each other in that way. Popular the graph-based databases on Neo4j, Azure offer their Cosmos DB offering, MongoDB. There are various ones. Use cases, social networks. For example, friend likes, Jane likes Jim, and she's also liked Mary and also Susan. Whereas, Mary has liked, I don't know, Isabel or whatever. So we can build up these network of relationships between people. Product suggestions. The person who bought that product also liked that, and that. So it might be the relationship is around the type of product, or it might be that this type of person might just be like you. And so we're going to recommend stuff to you because we think this person seems to like similar things to you. And you can build up relationships and profiles on people like this. You can use it for fraud detection. You can build up patterns of where the money's going, who's paying who's receiving money from where, and build up a picture that way. And GPS route mapping that I just discussed. So that's what a graph database looks like. Okay, we need to keep the data safe in the database, particularly if we've got personal data in there, or it might be intellectual property or whatever. And so we use encryption to scramble the data. So when you look at it, if you were to get access to the database, then it would look like random numbers. And what we do is we have an encryption key to used as part of the scrambling process. So you create a key. So when I say you, I mean you if it's your database, or an administrator if it's an organization. And it's usually some form of random number. Then you use that key and the data you want to scramble as inputs into an encryption program, and it will scramble the data based on that key. So to unscramble it, you need to provide the key again, and it'll unscramble the data back to a readable form again. So only the holder of the secret key can encrypt and decrypt the data. Particularly for sensitive data like personal data, company secrets, intellectual property, stuff like that. When the whole database is encrypted, the data is said to be encrypted at rest. Or any data that's encrypted on disk is encrypted at rest. So the data on the disk is scrambled. So if you actually stole someone's disk and tried to read the contents of it, it would just look like a lot of random numbers. It's all called, in database terms, transparent data encryption, because the database management system does it automatically. So when you write to the database with new data, the DBMS will encrypt that data and then save it to disk. Then when you request it back again later with a select star or whatever you want, then what it'll do is, as it reads the disk, it'll decrypt it and then send you the decrypted data. So it's transparent to you. You don't see it necessarily, you see it being used. Keys are usually managed by database administrators or some sort of security people who are trusted. By far the most popular encryption type for data at rest is the symmetric key encryption using the advanced encryption standard 256-bit key algorithm. So I'll give you a demo of that. There are various other approaches. Encrypting data in databases, it may well be you only want to encrypt certain columns like national insurance numbers or gender or whatever, instead of encrypting the whole table. But anyway, it's only an introduction this, so I'm not going to go any further than that. So let's have a look at what this cryptography looks like. So here I've written a little program to demonstrate this. So I've got something called, I'll just delete that file because that's what we're going to try and generate later. We've got private stuff. Got some private stuff here. So here's somebody's private bank details. What's the bank account number? What bank is it? Sort code, and whatever. And this person got loads of money in there, so they want their data protecting. So we want to be able to encrypt it. So to encrypt it, we need an encryption program. And this program could be a separate program, like I've just written here, or it could be a program that's built into the database management system, so it can just do the encryption and decryption on the fly. All right, so symmetric, what's this one? File, just get a bit wider and I can read them. Symmetric file encrypt. Right, don't worry about all this code. It's not relevant to this discussion, but I'll just point out a couple of important bits. What this program is going to do is it's going to read the file called privatestuff.txt. So it's going to read, where is it now? Privatestuff.txt. It's going to read that information from that file here. That's all that line's doing there. Well, it's not that line actually. That's just telling us what the file is, what the file name is. It'll read it further down. And what I want to do is I want the output file to be called privatestuff.enc. So you see we've got no privatestuff.enc, it's not there. I want to output the encrypted data into that file. So here's the way it reads the file. It's going to read the input file. It's then going to do the business on that input file and then write the output file. So here it's doing the encryption. And what type of algorithm they want to use? I want to use the AES-256 encryption method, which I just mentioned. Okay, I need a secret key. So here you can see I've got a secret key. It's just a random number. I didn't even write that down. I just got a random number generator to generate it. But because we're using AES-256, 256 means it's a 256-bit number. That's 256 binary bits. So given that each of these characters can hold 4 bits, we need 64 characters. So there are 64 characters there to give us our 256 bits. Right, so I'm going to use that key and feed it into this algorithm and generate nonsense, which is output to the output file here. So I'll run this. I've not tested this, I hope it works. Okay, so it says its file's encrypted and written to the private stuff.enc. And it's used that secret key there. Now obviously you wouldn't be advertising the secret key. I'm showing this as a demo. Alright, so that file should exist now. It is privatestuff.enc. Alright, well, it is quite unreadable. Let's see if I can open it in something that's slightly more readable. You see what it really looks like on the disk. It's just literally hexadecimal numbers, or binary numbers actually, but we're displaying them in hexadecimal to make it easier to read. And they're just random, there's just nothingness there. You couldn't make anything out from that. Right. So we now want to decrypt that data. So if I go to the decryption algorithm, decryption program, it's going to do something similar. I'm going to read the private stuff.enc, which has got the encrypted data in it. It reads it here. That's the name of the file. It reads it there. And then I'm going to use the same algorithm to decrypt it. I'm going to pass it the key there that I want to use to decrypt it with, which has got to be the same key that we used when it was encrypted. So if I run that, you'll see it won't work. Failed to decrypt the data because I don't have a secret key. I need that secret key. So it depends. If it's my secret key, well, I'll just get my secret key. I mean, I could read it from a file if I wanted to. If it's generated somewhere else, then somehow they need to securely give it to me so I can use it to decrypt information. And that's a whole nother security discussion. So if I go here and copy this secret key and use it in here, then hopefully run it again. There you go. It's decrypted our secret data into the readable form it was in the first place, or plain text as it's referred to. Very sensitive, these keys. You can change any of these numbers anywhere in the string. Let's change that 1 to a 0, and that's enough to stop it from working. Okay, so it's got to be exactly that key. Then run it. The key is exact. It works. Right, so that's encryption and decryption using a secret key, or a symmetric key, as it called this. The reason it's called symmetric keys because it's the same key that's used for the encryption as it is for decryption. There are other approaches like asymmetric encryption, which uses a different key for encryption than it does for decryption. But that's not anything to do with us today. All right, let's have a look at a bit more about data and databases. So data standards and quality is quite a big topic, but basically we're trying to, with data standards, ensure things like across the enterprise, all dates, for example, are in the same format. So it's day, month, year, as opposed to some of them being month, day, year, or some of them having 2-digit years and other ones having 4-digit years, because it means that if you receive data from one system into another system and it doesn't conform to the current system's data structure, then someone's going to have to change the data to make it fit. And unfortunately, because a lot of organizations don't have strict data standards in place, we have data engineers who are continually having to clean the data and reformat it into a form that is usable, say, for analytics. So, say, for example, an analytics department, they get data from 20 systems. They want to munge that data together to do analytics across the enterprise. They're going to have to make all this data match up so that day, month, and year are the same. Time is represented the same way. Names and addresses are of a similar format, etc. Why does it matter? Well, I'll just explain that. And it can be time-consuming, expensive, and can introduce errors by having to go through these tables and map them such that they are sort of standard across the different data sets that you're trying to analyze. So it's important that we have some form of data standards across the organization. Data quality is another thing that can cause problems. It's around how accurate is the data. Is it complete? Are all the fields present? So in other words, if an agent is filling in a form on a web-based user interface, and they don't type all the data in, and the fields are not mandatory, then you're going to end up with data arriving at the different platforms with bits of stuff missing. So the front end would have to enforce required fields. That's why sometimes you see a little red star next to boxes, and you've got to type something in it, otherwise it won't let you carry on. It's got to be consistent. So once it's passed from system to system, especially if it's been mapped in some way because of standards, then we've got to make sure that it's the same. And data consistency does have other implications as well. It's got to be timely data. In other words, you shouldn't really be using data that you received 3 months ago from a system, because that system will have updated its data by then. You should make sure that when you're doing making any decisions based on data, that the data is actually up to date. And validity, does it conform to specific rules and standards? And uniqueness, is the same data unique? In other words, it's not stored in two different places differently. So for example, somebody's told us on one system that they've got married, they've changed the surname, and they've changed it on that system, but other systems are still using the previous name. All right. In engineering, there are various ways we can improve data quality through programming. So front-end design is really important. You know, the HTML, CSS, and the JavaScript at the front end. So entries like postcodes, for example, phone numbers, national insurance numbers, and stuff need to be checked for completeness. Have you typed in only a 4-digit postcode, for example? You know, they don't exist. So we can check for that by counting the number of digits that have been input. For example, does the phone number look like a legitimate phone number? Are there enough numbers in it? We can avoid people typing stuff in manually and typing in incorrectly. So, I mean, sometimes even you'll see things like a drop-down box which says select a country. You think, well, I could just type in UK, but I've got to search through this long list of countries, and UK is towards the end somewhere. But you could type in capital U, capital K. Somebody else might type in U.K. and various other forms. That's only with 2 letters. So you can imagine how you can get other countries wrong. So we need some sort of consistent input. So selecting from a list is another data quality improvement approach. Street addresses. I mean, street addresses, it's very convenient that when you type in a postcode, it calls an API which accesses the database and pulls back all the addresses with that postcode for you to search for yours. It's handy for the user because you don't have to type it in, but it's even handier for the enterprise because you're not going to get people typing their address in multiple different ways. It's always going to be exactly the same way. All they have to do is select it, and that data will be consistent when it's been input. So the less we rely on user inputted data, the better, really. Much better to either check select from a list, or if somebody does type something in, call an API, call the back end to check it out and see if we find anything that matches. And if it doesn't, come back and say we can't match that name. You know, you might type a name in and you type it in lowercase characters. We store it in uppercase characters. Say, well, that's okay. We can convert lowercase to uppercase, uppercase to lowercase. We can do all sorts of transformations on someone's name. But if we don't find it because they've, say, typed in the wrong way around, they've typed in Smith instead of SMI, they've typed in SIM, so it doesn't say Smith anymore, but they've just sort of dyslexically typed the letters in. Then rather than us just accepting it and that looking like a new user, a new person, a new claimant or whatever, we'd look them up and say, no, hang on, we can't find you. Just check, have you typed this in right? They go, oh no, I haven't typed these 2 letters the wrong way around. It's that type of thing. there's lots of different methods to improve the data quality input from the front end. Accessibility is really important as well, because there are people who are blind. Some people who've got really poor vision, can see but they can't really see very well. Others might be colourblind, so they're looking at various instructions and they can't make out what they say because some of the letters merge into others, because of the colour scheme, for example. So we've already looked at this with the HTML. You can use the alt tags in the elements. So an image element, I can put an alt tag in there that describes the image. And so when a blind user is using the web page, they can't see the picture, but what the screen reader will do is it'll read out a description of the picture so they can visualize it. We use semantic tags as well, sort of title and heading 1, heading 2, heading 3 to enable the visually impaired users to visualize the structure of the document. And for people who are colorblind and other challenges, we can change the color scheme. We can make it black and white if necessary. I mean, it might not look very nice to most people, but for those who have got vision impairments, they probably don't care what it looks like. They just want to be able to see what it says. So we can simply have a separate style sheet for somebody. And if you have a drop-down box saying, are you colorblind? Yeah, I'll click this box and it loads a style sheet which changes the color scheme to better. It might not look as nice to the general user, but it'll at least be readable to the colorblind person. Or alternatively, you could avoid using those colors in the first place. But then there are other challenges that can be overcome by loading different style sheets in. I'm not going to get involved in the details of it. It's just an overview. All right, GDPR then. This is important with databases. General Protection Regulation. It's an EU-based initiative. I know we've left the EU, but it still applies to us. Improves data privacy. So collected data must be lawful and transparent. So you've got to give consent for people to use your data, or it might be contractual, or there might be a legal need to use your data, or there might be a public or legitimate interest. But generally, you need to give your consent. It should only be used for purposes that you've agreed to. So if you sign up to a website and say, give us your details to use this site, yeah, okay. But then they use those same details for something else, or pass those details on to somebody else, then that's in breach of data protection. Limits to only what's needed to provide for the service. So, for example, if they only need your name and email address, then that's all they should be asking for. They shouldn't be asking for anything else. If that's all that's required to operate the service. They've got to keep your details up to date. So they've got to provide a facility for you to be able to change your name or whatever else you want to change. And it should only be retained as long as needed. So once, for example, you've left a service of some sort, then your details should be deleted. You're going to make sure they hold them securely and protect against unauthorized access. And so one of those ways of doing that is to encrypt the data on the disk, for example, protect passwords and things like that. And the organizations must demonstrate compliance, and so GDPR assessors can check out your organization to make sure that you are observing the regulation. So it's your data, so you're empowered to access it, change it, to bring it up to date, erase it. If you want to have your data deleted, there should be an opportunity to do that, or restrict processing of your data. So the rights around automated decision making and personal profiling are limited within GDPR. So if you're applying for a loan, for example, and you've provided your information, it should be a human that really makes these decisions as opposed to automation. You can submit a free subject access request. If you're not sure what people hold on you, then you can write to them, just download the subject access request, say who it is you want to get access to the data from, and they will legally bound to send you what information they've got on you. And data retention, organizations should delete data once it's no longer needed. So for example, if somebody leaves the job, then it should delete their user details. All right. The final section on GDPR is where it is around the use of cookies. So cookie, stupid name, but anyway, the cookie is a small file of information that is sent to your browser from the server, and they're primarily used, or were primarily used, to enable you to interact with, say, shopping sites and such. So let's have a look what we've got here. It can be useful for internet, for useful intent such as keeping a track of when you add stuff to a shopping cart. So let's say that you log into Amazon shopping, and you what they'll do is they will create a cookie, which is a small file, and they'll generate they'll either look up your user ID if you're a user, or whatever, something to identify you uniquely, and they'll put that in the cookie, and they will send it to the web browser to be stored in your web browser. So every time you click a button on that website, it'll send that cookie to the back end. And the reason being that if you visualize this, there might be hundreds of people interacting with the Amazon shopping site at the same time. So they need to know who it is that's doing what. So when you press the button, the cookie gets sent in, and you might say add, I don't know, some shoes to your shopping cart. So that request comes in, the backend has to say, well, who is this? Oh, it's user whatever, because it's in the cookie that they've sent me. So they can go to a database, they create a database table for you, for your shopping basket, and they'll add in the shoes into that database. And then when you click something else, because you want, I don't know, some jeans, you click that, it sends a cookie. The cookie comes in with the request. So they'll look up your database table, and then they'll insert that pair of jeans into that request. Then when you say buy, again, it identifies you. It goes to the table, and it just looks up all the stuff you've ordered, and then contacts the inventory system and purchasing and payment and all the rest of them, then to go through the motions. They keep a track of you for a legitimate use. You couldn't even use shopping sites really without something like this. It might be just to remember who you are. So when you log in, a cookie is sent straight away. And if you've been there before, when you're registered, it knows, the backend knows who you are, so it can welcome you, say, hello, Mary, welcome back, or whatever else. It can remember your profile settings. You might want your web page to be set up in a certain way. And so the cookie can hold those settings. And so when you log in, it sends a cookie. They can look up what your settings are, and then when they return the web page to you, then it looks like what you wanted it to look like, as opposed to it going back to default settings, etc. So they're useful, very useful things. They're often used for analytics, advertising, or tracking your online activity. Not always so useful. So GDPR now requires consent to be given for doing this for every site you visit. So we've got essential cookies like these, and then we've got other ones that are not essential, but they would like you to use them. It might be not necessarily nefarious. It might be a case of, look, we're going to send you adverts, so you've got an option here. Do you want us to send adverts that are more likely to be of interest to you, or do you just want to send them random adverts? You know, we're not going to stop sending adverts, but if you select this option, we'll send you targeted advertising. So it might just be something as simple as that. Or it might be that every time you click the button, the website you've connected to is also making that information available to other companies, and they're building up a profile of your web activity. You may be bothered, you may not be bothered. Some of them use them for analytics, like how long did you stay on that page before you bought something, or how long did the page take to load? Did you actually leave the page because you got sick of waiting? How quickly did you find what you wanted? How long did it take for you to click something and then go to payment? So they can measure their own performance through gathering this sort of information. So quite often these are first-party cookies. In other words, they are cookies provided by the website that you're interacting with, or that you've signed up to. But they're also third-party cookies. These are cookies that they can send to your web browser on behalf of other people, other organizations, and there can be lots of them. So if you're a bit lazy, and whenever it comes up with a GDPR thing, you think, oh, sick of these GDPR cookie things, I'm just going to say, yeah, okay, whatever. Yeah, I agree, crack on. But you don't really know what you're agreeing to. So it should be, now, GDPR-wise, it should be easy to accept or reject cookies. They should really say, do you want to reject all cookies? Do you want to accept only essential cookies? Or do you want to accept other cookies like analytics and third-party cookies? It should be absolutely clear. But obviously, a lot of sites try and hide this and try and trick you into accepting these things. Okay, now you might think, well, they're only gathering analytics from me. You know, how long does it take for me to click a button and that sort of stuff? But if you've got loads and loads of these things, it could impact the speed at which your pages load, because you're sending loads of stuff out to loads of different organizations every time you click something. So bear that in mind. Okay, so I just said this GDPR. Insist on permissions being simple and clear. Not everybody adheres to it, even though, because we're in the UK, everybody should, no matter if they're outside the UK or not. But they don't. Many people are lazy and just say, yeah, all right, whatever. And some users deselect all the third-party cookies by default, and you have to select them in. But now they've got around that by something called legitimate interest, and they've started pre-selecting them. When they talk about legitimate interest, they're not talking about your legitimate interest, they're talking about theirs. So let's have a look at a couple of these sites and see if I can trigger these cookie requests. So I'll try this one. This has probably got a cookie blocker built into it, because I use this one for such things, but let's give it a whirl. So here's one that I think, if it'll show me, is not even legal. So this one is a Superbikes site, and if you look, here's the cookie, the GDPR required cookie question, and all it says is, I understand. We use cookies to understand how it's used, blah blah blah. Click I understand. Well, that is definitely not in line with GDPR, because you should be able to say, no, I'll just carry on without cookies. I don't want to just say, yes, I understand. I want to know what you're using them for. So I think that's either illegal or they're sailing very close to the wind. I wouldn't even use this site if they were doing that sort of thing, because you think, well, if that's what they're doing from the website, what else are they going to do when you're buying stuff, especially when things are expensive? Let's try this one. There's another motorbike site, but they've got here, we use cookies. and they give you quite a reasonable question. Only website uses cookies in order to enhance the overall experience. Okay, I only want essential ones to use the site. Accept all. You think, well, what does that mean? Accept all of them. Well, you can customize them. So that should give you more information about what accepting all actually means. I just clicked on customize and it's just disappeared. There's nothing there for me to customize. I don't know where it's gone. So let's refresh this page. It's asking me again. Let's try clicking this little arrow and see if that's any different, because sometimes it matters where you click stuff. No, it's just not giving me the chance to customize. And so, in other words, although it's made it look like it's easy, I can either only pick that one or that one. I can't actually change these, select ones I want and ones I don't want. Here's one. If it'll work on here. This one, okay, that's something different. So this one, all right, this site's blocked it. So let's just I'll try a different browser. Let's see. That browser I was using quite a secure browser. Let's just use the usual Chrome browser or Edge. So let's find a page. Let's try and drag it on here. Come on then. All right, so it's asking me, do you want to consent to everything? No, I don't, thanks. All right, I'll manage my options. Let's see what you've got to offer me. Well, I've got the 121 vendors turned off here, but you can turn them on if you want to, like you would. But look at this. There's another 74 vendors that are turned off, but these that they're calling legitimate interest, 39 different people want to register legitimate interest cookies, and that's actually turned on. So you have to turn that off manually. And then down here, you think, oh, well, that's just that one. That's not so bad. Keep going down. There's another 55 people here. They want to push cookies your way. No, not good. Another 20 here. Another 28. Another 48. And you think, oh, really? You can't be bothered doing all this. And so you think, oh, but I really want to use this site. So you've either got to go through the laborious method of doing that, or accept all and take choices. So I would go down there, deselect them, and then click confirm choices. I'm not going to, because I'm going to use this page. You can, some browsers will allow you to disable third-party cookies. Take Chrome, for example. You can go to, you got to dig deep for it. Settings, privacy and security, third-party cookies. It says here that they're blocked. You go into there, and then you can select third-party cookies being blocked. So, in theory, if you accepted them, this should block them. Any of those third-party ones. Okay, so that's about it really. I think that pretty much covers everything I wanted to cover on databases. So I hope that was of value to you, and it's a little bit long, but I did sort of spend a bit longer explaining stuff. So, okay, until next time.